All right, so here we go, walking through the practice test. I'll try not to go too fast, and feel free to just skip around and find the problems you have questions about, okay? So we'll start here. This first page is on trig, although it's really closely related to that idea of splitting an isosceles or equilateral triangle down the middle, which we use a lot when dealing with regular polygons. So the first one says find the height of this triangle. Well, I notice that it's equilateral, so I can go ahead and write 12 for each of the side lengths. And the big idea is an isosceles triangle, and equilateral too, has that line of symmetry down the middle. So we can draw that perpendicular bisector, and that perpendicular bisector down the middle cuts the angle in half, cuts the angle at top, which was 60 because it was equilateral, so all the angles are 60. But it cuts the top angle in half to be 30 and 30. I'm going to zoom in a little bit here, so we're just focused on this one problem. And then we can go ahead and also split that base in half. So here's a length of 6 and the length of 6. Okay, so first thing it says find the height of the triangle. Then it says find the area. Well, off to the side I can say, well, I know the area is 1/2 base times height. So I know the area is 1/2. The entire base is 12 times, and now I just need to find what that height is. So, okay, so we need to find that height first. So you got two ways to do this. You can either notice it's a 30, 60, 90 triangle. So you can say my triangle here that's got a 60 and a 30 and a 6 and a 12 here. I'm dealing with half of this entire triangle. That's similar to our standard 30, 60, 90. Notice I orient it the same way as my original. So across from the 30 is the 1, across from the 60 is the √3, and across from the 90 is the 2. So I could say, okay, these are proportional, and I could say, well, you know, gosh, this is just a factor of 6 to 1, right? We multiply by 6 to get from 1 to 6, 2 to 12. So this side must be 6√3. So that's kind of a shortcut way. Another way is you could use Pythagorean Theorem. We have two sides here, so we could say 6 squared plus height squared is equal to 12 squared, and that would get us our height of the triangle. Another way is to use trig. We could say, okay, well, either the sine of 60 degrees is equal to h over 12, or the cosine, or the tangent of 60 degrees, which would be opposite over adjacent, would be our height over 6. There's so many ways to solve this, either 30, 60, 90 triangle, Pythagorean Theorem, or trig. And what we end up getting is that the height of our triangle is exactly 6√3, or the height of our triangle is approximately, I'm going to write 6 times √3, or approximately 10.392. Okay, so I'm going to deal with the exact answer up here, or you could be plugging that 10.392 in here. So plugging that in, I get that this is, the area is, well, 1/2 of 12 is 6. And then times, I'm going to plug that new value in. So I know we found our height to be 6√3. So I know our height is or our area is exactly 36√3. But that comes out to be approximately, and what I'm going to do off to the side here is go 36 times square root of 3, or just plug in the 10.39 in there, and we get 65. I'm going to round it to 2 decimal places. 65. Why did I say that? 62.35. So 62.35. So there's an exact answer and an approximate answer. The original problem didn't specify. I purposely, on the entire practice test, didn't specify exact or approximate, so you could do either one. On a quiz or test, I would be very clear what I'm expecting. Okay, I want you to practice what you're most comfortable with. Okay, so here's an isosceles triangle where BC is 20, and measure of angle B is also 20. Okay, so I know base angles are congruent. I know it's an isosceles triangle, so I can cut it in half. and I get a length of 10 on this side, a length of 10 on this side, and it says find the area of the triangle. Oh, so again, I know that the area is 1/2 base times height. So I know the area is 1/2. We have a base of 20 times, and again, we're looking for that same height. So simplifying that, that's 10 times, and we're going to have to go about finding the height of this triangle. Okay, so in this one, you don't have as many options. So here, what we've got is, we've got an isosceles triangle split in two, which gives us a right triangle with a 20-degree angle, which of course we could subtract from 180 and find the other angle 70. We don't need that, but we can put it in there. And we do know that the bottom side here is 10. So we know all the angles in a triangle. We know all the ratios, the proportions. It's similar to every 20, 70, 90 triangle. Now we can use that size of 10 to say, now I know exactly how big our triangle is and its shape, so I can use trig to find every other side. Now we don't care what the hypotenuse is over here, but we do care what the height is. Because once we find that height, we can just plug it in over here. So below this, I'm going to say, well, if I'm choosing my 20 degrees, this is my opposite side, this is my adjacent side. So I've got the tangent of 20 degrees is equal to h over 10, or multiplying by 10 on both sides. I get that my height is exactly 10 times tangent of 20 degrees, or my height is approximately, so 10 times the tangent of 20 degrees. Oh, I shouldn't have put the degree sign in there. So 10 times tangent of 20, 3.639. So 3.639. Now, again, I'm going to keep the exact when I go up here. You could absolutely use the decimal version. I just like exact answers. So this ends up coming out to be 10 times 10 is 100 times the tangent of 20 degrees. That's the exact value, which I'll always accept, or that's approximately, and over here, I'm going to say this is, I'm just going to add a 0 in there. Can I? Let's see. Oh, it wouldn't let me. Okay, so let's just write it out. 100 times tan of 20. Okay, so, oh, I could have just multiplied that by 10 by moving the decimal. 36.39, and notice I didn't round in the beginning. There's a 7 after that. So that's 39's going to round up. So I'm going to get 36.40. So 36.40. So my area is either exact or approximate. Okay. Now moving on to number 3, a very similar problem. This one gives you instead this side is 10 AB. So the other side obviously is 10. And the top angle is 60. So notice that I can split that in half, and I get that the base gets split in half too, because this is an isosceles triangle. So I get an angle of 30 on each side, and subtracting, what I end up getting is a 60. So what type of triangle is it with 60-degree angles in all 3 angles? This was another equilateral triangle. So without any work, I can right away say, oh my gosh, an equilateral triangle, this base is also 10. So this side here is 5, and this side here is 5. Okay, so again, oh, this one only asks for the height. It doesn't ask for the area, so we didn't actually need that. Okay, so this time, again, you could use trig. You could use Pythagorean Theorem. I am instead going to choose to use a 30, 60, 90 triangle. We haven't done that in a while. So I'm going to say, all right, so what I've got is I've got a triangle like this, 60, an unknown height, and a side of 10. Let's pretend you didn't notice that it was an equilateral triangle. Okay, so that's what's given. Okay, this was 30 degrees. This is 90. All right, well, I know this is similar to every 30, 60, 90 triangle out there. So here's 60 degrees, here's 30 degrees, and so 1, √3, and 2. So I would set up a little proportion. I'd say, okay, so h is to √3 as 10 is to 2. Now, if I want to get rid of that divide by √3, I'll multiply by √3, and that'll get, you can cross multiply here, But I know just one step here and I'm done. Because if I multiply by root 3, I'm done. H is equal to, so H by itself is equal to 10 divided by 2, which is 5 times root 3. So H is exactly 5 root 3, or H is approximately, and off to the side here, I'll say 5 times square root of 3, which is 8.66. Okay. Again, exact or approximate. So now this one says solve the right triangle. So when it says, or it just says solve the triangle. When it says solve a triangle, what it's saying is find every single every single angle measure and every single side length. So let's look at this. Well, we know two sides, so let's just get the other side, okay? I'm going to choose Pythagorean Theorem. That's easiest for me. 4 squared plus 7 squared equals c squared. I could do that because there's a right angle. So that gives me 16 plus 49. That's 59. 65 is c squared. So c is square root of 65. I'll go ahead and write that up here. Square root of 65. I will also approximate that for those of you that like working with decimals. So square root of 65. That's 8.06. Now notice, though I'm abbreviating it right now to 8.06, if I use that value in the rest of my problem, I will use the longer decimal or the exact square root of 65. I will not use my shortened 8.06 to find other values in the problem. That would make my error margin increase and increase, and my end decimal be off by a little bit. So I would use a more precise C value or exactly square root of 65. But anyways, we're done with that. We already have the length of AC. We already have the length of CB. So we've got all three sides. So now we need to find the angles. Well, obviously, we already have the measure of angle C. That's 90 degrees. So we're really looking for the measure of A and B. So if I call this theta or A or X or whatever you want to do, well, I know with regard to that angle, the tangent of that angle is equal to the opposite side 7 over the adjacent side 4. Or I could have used the square root of 65. I could have said the sine of that angle, right? The sine of this angle would be equal to the opposite 7 over the hypotenuse 65. So I could have used these three in the sine, or I could have used these values in the cosine. So you can choose any trig function you want since you have all three sides. But because the 7 and the 4 are so precise and accurate, they're exactly integers, I'm just going to use those two. Okay, so the tangent of that angle is 7/4. So I know it came out of the calculator, but I want to go backwards. I want to do the inverse. And so what I'm going to say is, well, that means then my theta, the actual angle, is the inverse or arctan, or you could say tangent to the -1, of that ratio. So if I use the regular tangent, it goes from angle to side length, or side ratio. If I use the arctan, it goes from the ratio of the sides back to the angle that gave you that. So the arctan of 7/4 over here, I go arctan of 7/4. That's 60.255. I'm going to round that up, so 60.26. So theta is around 60.26 degrees. So there's an exact value and an approximate value. So once I know that, oh, why did I use theta? Let's go ahead and erase that. Now that I have solved for theta, let's go ahead and call that the measure of angle A. The measure of angle A. That was the angle we found. Okay, well, if I want to find the measure of angle B, well, the measure of angle B is just you take A and C away from 180. Or, you know, we know measure of angle A and measure of angle B must add up to 90 in a right triangle. So I'm just going to say the measure of angle B is 90 minus measure of angle A. And so 90 minus 60.26. And again, since I am actually using that value to find a new value, I do not want to use the shortened version. So I'm going to go over here and I'm actually going to use the exact value. I'm going to say 90 minus the arctan of 7/4, which I know the arctan of 7/4 is at 60.255. Okay, so I am getting, oh shoot, they couldn't read my nines. My nines are so rough. Okay, there we go. So we get 29.74. Okay, so 29.74, so measure of angle B is around 29.74 degrees. But guess what? I'm going to double check that a different way. I'm going to, just because I like double checking my work, making sure it's correct, I'm going to solve it the way I solve for A. I'm going to say, well, I know that the tangent of angle B should be equal to 4/7. So I'm going to say that the measure of angle B then is the arctan of opposite side 4/7. I'm just going to double check what comes out, okay? So arctan of 4/7 is a quick double check just to make sure we did everything right. 29.74, great, so it checked out. So the measure of angle B is an exact value, would be that, or the approximate. And now I have all of my angles, all of my sides. I'm done solving the triangle. Okay, let's move on. So answer each of the problems true or false, okay? If you respond with false, give an explanation or counterexample. So the diagonals of a rectangle are always perpendicular. So that is not necessarily true. That is sometimes true. So I'm going to go ahead and write false. They are not always perpendicular. And here's an example, right? I'm just going to make a long, skinny, oh yeah, I could do straight lines. That's even better. So I'm just going to do a long, skinny rectangle here. So here's, you know, something like this. Whoa, it didn't draw it for that time. Let's see. Okay. And then, shaboom. Okay, I'll just finish that off. So if I draw the diagonals here, obviously they are not perpendicular. Now you could argue, oh, it's not drawn to scale. They're actually perpendicular. Well, let's make up some values then. If this is an 80-degree angle, I can find every single angle in this image. Well, that means this is 80 degrees because the diagonals are congruent. That's what makes the parallelogram stand upright and be a rectangle. And since every parallelogram's diagonals bisect, we know all of these are congruent. So all of these form isosceles triangles. So that's 80, 80. Since we have a 90-degree angle here, we know the sliver is 10 degrees. Sliver is 10. Isosceles triangles, there's a 10 over here, 10 over here. A 90-degree angle in the corner means this is 80. This is 80. We could then find the missing angles in the middle because triangles add up to 180. So 80 plus 80 is 160. So the leftover is 20 degrees. 10 plus 10 is 20, so the leftover is 160 degrees, 160 and 20. So there's an example of a rectangle where the diagonals are not perpendicular. Okay, kites always have two lines of symmetry. Oh, well, that's definitely false. Everything we know about a kite comes from the fact that it is an isosceles triangle glued to a different isosceles triangle. And so, yeah, it has one line of symmetry. I could cut it this way, right? I could definitely cut it across that way. Now, that was a terrible cut. But I can cut it that way, and I do get by side, side, side. That's a line of symmetry. The two triangles are congruent. But if I were able to cut it another way, like, for example, this way, then it would be a rhombus. So you can't cut it that way. If I was able to cut it this way, well, that would change everything. Because that would be, what? That would be either a rectangle or a trapezoid, depending on which thing stayed the same, but it definitely wouldn't be a kite anymore. So a kite definitely only has that one line of symmetry that cuts the two isosceles triangles in half. Okay, so one line of symmetry, not two. Consecutive angles in a parallelogram are always congruent. Well, I know a parallelogram's opposite sides are parallel, so I know that there's a 180-degree turn between consecutive angles. So I know they're supplementary, but if they add up to 180 and they're congruent, then two things that are the same that add up to 180, they must be 90 plus 90, right? These would have to be right angles. So this isn't always true, but it is true if it is a, right? If the two angles are 90, if it is a rectangle, or if it's a square, that would be true. But the angles are actually, in this, they're actually supplementary, not congruent, okay? And you could make up some numbers here. You could say this is 70 degrees, so then that would make this 110. This would be 70 because opposite angles are congruent. This would also be 110. So there's an example of a parallelogram where the consecutive angles are not congruent. The diagonals of a rhombus are not congruent. Again, this is not true. So we know that a rhombus is a parallelogram. And if a parallelogram has diagonals congruent, that's like taking a rickety old bookshelf and tightening the two diagonals until they're the same. The bookshelf then ends up standing upright. And that's one way to keep a bookshelf rigid from tipping over, is by putting some cross braces. So like you see it on gates. Often, wooden gates, like for a yard or a fence, have those cross beams. And that's so the, rectangular gate doesn't start tipping and be more diagonal and start rubbing on the wood, not opening and closing so nicely. So let's fix this one. I mean, obviously, let's see. I'll draw this this rhombus. So there's one super long diagonal and one short one. And we could, to make this, I mean, that is one, let's say this is of length 4 and this is of length 40, right? Well, all of these sides, I could just say, well, since these get split in half, here's 2 and 2, here's 40, and let's even make it 40 over here. I could use Pythagorean Theorem to find out C here, and 2 and 40 would give me the same 2 and 40 over here, the same 2 and 40 over here, 2 and 40. So Pythagorean Theorem, all those lengths would be the same. So that is a rhombus. And that is definitely not, the diagonals are definitely not congruent. It's 80 versus 4 long, so definitely not congruent. So this is false. Okay, so a tangent line to a circle is perpendicular to the radius at the point of tangency. That is true. If we have a radius of a circle and a point or a line is tangent to the circle at that point, it does make a 90-degree angle. So that one is true. The mid-segment of a trapezoid is always parallel to both bases. That is another one that's true. No matter what the legs look like, if we connect their mid-segment, the midpoints of the two sides, it is parallel to the basis and the average of the length. Right? We actually use that to find the area of a trapezoid. Okay, so the opposite sides of a parallelogram are congruent. Now, I believe this is the one that was different. On your version, there was actually accidentally a duplicate of A. The diagonals of a rectangle are always perpendicular. So one of these I changed. So one of these will look a little different than your version. But the opposite sides of a parallelogram are always congruent. Oh, that's true. That's one of the properties we know. I mean, we could go back and prove it by splitting this into congruent triangles. But let's not do that right now. We do know that the opposite sides are congruent. We know that opposite angles are congruent, so that is always true about parallelograms. The opposite angles of a rhombus are always congruent. Yeah, that's always true. And that's because we know it in general about a parallelogram. And since a rhombus is a parallelogram, then it's definitely true about that. So yeah, the opposite angles are always congruent. Okay, so translate the triangle below by the vector 5, 3. So that's in terms of x, y, this is moving right 5 and down 3. So let's go ahead and do this. So right, I'm going to move k first. 1, 2, 3, 4, 5. 1, 2, 3. So k would go right here. L will go 1, 2, 3, 4, 5. 1, 2, 3 right here. And notice how they still have the same relationship. It was this down 2, right 2 from k to L. It's still down 2, right 2 from k to L. So same line segment, just got moved over and down. So J is going to go 1, 2, 3, 4, 5. 1, 2, 3. Goes down here. So then I connect them. Here is my shape. I'm going to actually just fatten up my pen here. So this is K prime, L prime, and J prime. Let's switch over to pink so it stands out a little more. So reflect the triangle over line y plus, or y equals x plus 2. Okay, so we got to remember how to graph this line. Now, first of all, I remember it as mx plus b. So the slope is 1, or 1 over 1, and the y-intercept is 2. So I remember it as go to 2 on the y-axis and go up 1, right 1, up 1, right 1, up 1, right 1, and so on. Now, if you've totally forgotten that, okay, there's a lot to remember, so many things in math. So if you've forgotten that, your backup plan is to make an XY table. Okay, so I'm going to go over to the side and say, you know what, I've forgotten everything there is to know about graphing. But I do know one thing, and that's if I plug in an X, I'll get its partner Y value. So if I plug in 0, I get, up top here, Y equals 0 plus 2, so Y must be 2. If I plug in 1 for X, then I get Y equals 1 plus 2, or 3. If I plug in 2 for X, I get 2 plus 2, so Y is 4. And then I could go to my graph and I could just plug those in. 0, 2, that's a point. I get 1, 3, that's a point. I get 2, 4, that's a point, and just connect that with a line. Okay, so that's one way if you've forgotten everything to graph it. So if I want to reflect this triangle over it, then what I'm going to do is I'm going to say, okay, I need to go directly perpendicular to this line, straight at it. So from any point, the slope perpendicular to my diagonal is the other diagonal. So I need to go directly that way. If you have a vertical mirror, you go perpendicular to it by going horizontal. If you have a horizontal mirror, you go perpendicular to it by going vertical. If you have a diagonal, the other diagonal, if you have a slope of 1, the other diagonal or slope of -1 is perpendicular to it, okay? So let's do this. We got L is 1 diagonal away, so we'll go 1 diagonal to the other side, and here is the new L, okay? K was 1, 2, 3 diagonals away, so 1, 2, 3 diagonals away over here. J was 1, 2, 3 diagonals away, so 1, 2, 3 diagonals away on this side. There is my J. So I'm going to go ahead and erase those, okay, just to get rid of the mess. Oh, it's because I made it all one point. I need to do that again. So 1, 2, 3, and 2. There we go. Okay, so there is my new shape. I will label which points came from where. So this was my L, this was my K, and this was my J. And then if you turn this shape, and I'm just going to do it really quick, if you just rotate this, oh wait, I could do the whole thing. If you just, it's a PDF, so I can't rotate it right now. So if you were to rotate this, I'm visually like turning my iPad in front of me, but if you rotate this, so the diagonal line is now vertical, it should look symmetrical to you. So you could just turn your piece of paper and go, oh yeah, that looks like a set of butterfly wings or something. Like that does look the same on the left and right of that line. And because your eyes are set the way they are, it's easier to see visual in a vertical setup than it is like diagonal. You have to kind of turn your head. But you should just check, does it look symmetrical? If it does, you're like, great job, okay. So rotate the below 90 degrees around. So first I'm going to say, okay, my point that I'm rotating about is this point down here. Okay, -1, -3. And 90 degrees clockwise. So ballpark, it's going to go from here to something over like in this region. Like ballpark, that's 90 degrees. Distance stays the same. So that's just, in the end, it should look something like that. Okay? So I'm going to rotate this by finding a path to each point, okay? So I'm going to say I went up 1, 2, 3, 4, 5, 6 to get to L. So I'm going to turn that path 90 degrees and say I went over 1, 2, 3, 4, 5, 6. Here's my new L, okay? All right, so that's my L prime. Now if I want to find K, then I'm going to say, okay, well, to get to K, I went up 1, 2, 3, 4, 5, 6, 7, 8, and over 2. Okay, so 8 and 2. So it's a little L, so it looks like this, 8 and 2. And what I'm going to do is, keeping this point where it's at, I'm going to rotate that 90 degrees. So let me try that again. So I'm going to rotate that, come on, 90 degrees. So I'm going to rotate that 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 90 degre I'm going to rotate this 90 degrees like this. So I'm going to keep my finger on this point and I'm going to rotate it. See how it's rotating 90 degrees? 90 degrees, it'll look like that. It was here, 90 degrees. So I have an 8 and 2. So that's what I'm going to do. I'm going to go over 1, 2, 3, 4, 5, 6, 7, 8 to the right and up 1, 2 to get my new point, and that's my K prime. Okay, I'm going to do the same thing for J. I'm going to say, you know what, let's do a different path. This time I'll go left and up. So let's go left 1, 2, 3, 4, 5. Let's go up 1, 2, 3, 4, 5. So now I'm looking at a path like this. Over 5, up 5. Okay, and again what I want to do is I want to rotate that. So I'm going to keep my finger on that point and I'm going to spin it and write 90 degrees clockwise. So like a clock, it started like this. The thing that was pointing at the 9, coming from the dot, that's pointing to the left, like 9 on a clock, I'm going to spin that until it's pointed at the 12 on a clock. So it went from pointed left to now it's pointed up. So here's my set of instructions to get to my new point J. So I go up 5, 1, 2, 3, 4, 5, whoops, and then over 1, 2, 3, 4, 5. And there is my new point. So that is my J prime, and I can draw my triangle now. The points should still have the same orientation with one another, and ballpark, that's where I wanted it to go. So I'm just going to erase all my paths that I drew here to get to my shapes. And there you go. That's my final product. Okay, you can also use patty paper, a compass. You use so many ways you could do this. Okay, so I'll erase my paths that we did. So now dilate the shape. Now what dilation is simply if I have a center and I have a point, however I got to that point, let's say I went up 2 and right 4, I just multiply both of those with my scale factor. My scale factor is 3, so I'll go times 3 times 3, and so instead I will go up 6 and right 12. That's like going 2, 4, 2, 4, 2, 4. Either way, you went a total of up 6 and right 12. So you're really just saying do 3 steps from that center. So go 3 times as far from the center. So I have the center at -6, 5 here. And I want to project each of these points 3 times as far from there. So to get to K, I originally went over 1, 2, 3. Okay, so I'm going to multiply that by my scale factor of 3. So I'm going to go now a distance of 9. Here's the key. It's still away from my center. That's the mistake a lot of people make, is they start at the point K. You don't want to do that. You want to go back to your center and say, I was a distance of 3 away. Well, now, along that same direction, I want to go a distance of 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's where I want to end up. So my new K, or K prime, ends up here. Okay, now what I want to do is go, okay, well, how did I get to L? Or J, let's do, that's easier. I went down 3. Well, again, starting at my center, now I want to go 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3 times as far. And my new J prime is down here. And then L, it's got, go down 2 and write 1, 2, 3, 4, 5. So it was 2 and 5. Let's see, 1, 2, 1, 2, 3, 4, 5. Yep. So I'm going to multiply that by 3. So now I'm going to go down 6 and over 15. Okay. So let's do that. So I'm going to go down 1, 2, 3, 4, 5, 6 from my center. And I'm going to go over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I'm out here. Here's my new L prime. Now, an easy way to double check is if I connect my center to my new point, I should go right through my old point. And look, sure enough, it does. It goes right through there. So I projected it outwards in the same direction 3 times as far. So now I've got, here's my new triangle. It should look just like the old one, but be bigger. Okay, so I'm going to go back and erase my scratch work here. So all these numbers and counts, okay? There's my new shape. Again, we dilated it around a specific point. We didn't dilate it in any place we want 3 times as large. We projected it outwards from that point. So it went out from that point, okay? So find the indicated measures. Okay, so I just as a checklist, the order I go in here is I say, okay, do I have any inscribed angles? Okay, do I have any inscribed angles? No, I don't see any. Next thing is, do I have any half circles as 180, or do I have any total circles being 360? You know what I do? If this is 55, and this is 74, and this is 68, I can find the remaining simply by saying, what's 360 minus 55 minus 74 minus 68? The remainder is 163. So I know the last arc here is 163. Oh, and that was the very first question. So 163. Great. Okay, so now I'm out. I've got no other semicircles, full circles. I've got no inscribed angles. Okay, so my 2 things I check the most are done. Now, the next thing I check is, do I have either an angle not at the center on the inside of the triangle, or do I have an angle outside my triangle? Or outside my circle. Oh, I do have this situation. And I know the way you deal with that is the arc, and just I'll draw one down below, is I know if I have 2 lines that intersect not at the center, that angle they intersect at, which vertical angles is the same on both sides, is equal to the average of the arcs. So here x is the average of a plus b. So in my problem up here, I know that this angle here, x, is equal to 1/2, that's 68 plus 55. So I'm just going to go over to the side with my calculator, and I'm going to say, what's 68 plus 55? And then once I get that 123, I'll divide it all by 2, and I'll say 61.5. So that angle is 61.5. Does the question ask for that angle? Well, I mean, once I have that 61.5, I could say, well, it's the same 61.5 on the other side. And since this is a straight line, this angle is just 180 minus 61.5, which is 118.5. You could use a calculator for that. Let's see what it asks for. So we found seemingly everything. So AEB. Oh, yeah, AEB is 61.5. That's the one we just found. Then AED. Oh, that was the second one. That's just because it's a straight line. It's just 180 minus that. So that's 118.5 degrees. Okay, now let's use the same steps. Oh, no, that was the only circle problem. Oh, okay. Oh, no, circle problem right below. There we go. Okay. We'll come back to the length arc. Let's use that same process here, okay? So let's use first inscribed angles. Okay, let's see. Just relabeling this. This is 70 degrees and 92 degrees. Okay, so first off, do I have any inscribed angles? Yes. Angle 1 is half of 92. And angle 3 is half of 70. Okay, no other inscribed angles opening up to something I know. Okay, now do I have, and again, that was the first thing I checked. Second thing, do I have any half or complete circles? Well, on top, I have a half circle. So this arc over here is just 180 minus 70. So I know this is 110. And on the bottom, I know this arc here is 180 minus 92. So this is 88. Okay, and then let's see. Oh, back to now inscribed angles. Now I have angle 6 is half of 110. And okay, so that's that. Now I could just use subtraction here to find angle 2, but actually I know that this total arc down here is 180 degrees because it's a half a circle. So angle 2 is half of that because it's inscribed. So angle 2 is a 90-degree angle. Let's see, what else do we have? Oh, angle 4 and angle 5, we don't need anything tricky for that. That's just the central angle, right? From the center, out of that 360 degrees, 92 of the degrees are this portion of the circle. So the central angle is equal to the measure of the arc. And angle 5 also, it's equal to the measure of the arc. That's just 88 degrees. Well, that's a fun problem. I like those problems. Okay. So going over to 13, we've got, oh yeah, so I don't see any inscribed angles because, I don't have any arc that this is opening up to. I don't have the arc this is opening up to. I don't have any half circles, like the center would be somewhere around here. It's not drawn in. I don't have enough information to find missing things from the whole circle because I'm missing 3 separate arcs. Okay, so let's check the next thing. The next on my list after inscribed angles and half circles or full circles is are these 2 weird situations. Do I have a random angle inside or outside of my circle? Ooh, I do. I have a 50-degree angle here. Well, I know that situation is if I draw it like this, I know that X, A, and B have the relationship where X is 1/2 the big arc minus the small arc. So if I label this arc on this far side over here, if I label this B for big arc, well, I can plug in values here. I know that the angle outside is 50 degrees, and that's equal to 1/2 the big arc minus the small arc is 25. So I can just use some algebra to solve for that big arc here. So that big arc from W to A is going to be, and let's times by 2 on both sides just to get rid of this fraction. So 100 equals B minus 25. Adding 25, we get that B is 125 degrees. Okay, so this is 125 degrees from W to A. Well, we also know that, and it's asking us to find measure of WAB. Well, we know that whenever we have a tangent to a circle, doesn't matter if it's the diameter where it's 90 degrees or if it's any other tangent, this angle here is really an inscribed angle of the arc, right? 90 degrees is half of 180 because it's an inscribed angle of that arc. Well, this one is half of that. So if this arc here is 25, then this angle WAB, is just half of that. So the measure of angle WAB is just 1/2 of 125. And so 125 divided by 2, the measure of angle WAB is equal to 62.5 degrees, okay? Perfect. You'll hear a bell in about a minute. I'm just going to keep working as we're almost done here, okay? So to find the length of the arc and the area of the sector, well, for both those, I just need to know a fraction of the circle. So for the length of the arc, we've got 60 degrees out of 360 times the circumference of the circle. So I've got 1/6 of, and the circumference of the circle, just plugging in a 9 here for radius, is 1/6 of 18 pi, or that's 3 pi. So that was nice. So just what fraction of the circle do we have? We have 60 degrees out of the whole 360. So I have 1/6 of the circle. And I know all the way around, the circumference here is equal to 2 pi r, or 18 pi in this case. So I just find out what 1/6 of 18 pi is. And that's the length of this arc from P to Q. Okay, and we're going to use the same logic here. And of course, you could plug that into a calculator. 3 times pi. So 9.42. Okay. You could also use the same logic down here and say, well, I have 60 out of 360 degrees times the area of the circle. Or in other words, I have 1/6 of, and the total area here, if I plug in 9, is 81 pi. So 1/6 of 81 pi, just do a little simplification here. 3 goes into both of those. So we get 27 pi on top and a 2 on the bottom. So an exact version would be 27 pi over 2, or that would be around 27 times pi over 2, which is 42.41. Okay, so both cases, you were just simply saying what fraction of the circle do I have, and then times the total area, or what fraction of the circle do I have times the total circumference. Okay, so last page here. Find the area. Is this? Oh, second to last page. I'm sorry. So I'll actually stop here, and I'm going to resume this a little later in the day because we're out of time. I hope you enjoyed the video. Okay, sorry for the interruption. So let's see. We got find the area and perimeter of the shapes below. Okay, so we're given this as a trapezoid. So we know the top side is parallel to the bottom side. Well, that means a right angle here means a right angle at top. And of course, we can always draw a perpendicular to a line. So let's draw the perpendicular to the bottom here, the altitude kind of from that point C. And because those lines are parallel, we know this is a right angle. So this is a rectangle. So we know there's a 15 down here, and whatever this length over here is, it's the same as over here. So the area of a trapezoid is 1/2 base 1 plus base 2 times height. So right now all we've got is one base is 15 plus we don't know the second base on the bottom because we don't have this length here. Okay, and then times, and we need the height, and so we need this length here. Now notice if I could find this height over here, it's the same as over here, and I have a right triangle with two values, so I can use Pythagorean Theorem to find that. Then once I have that height, I can say, well, look at this. If I've got the height and I've got the 20 and a right angle, I could use those two with Pythagorean Theorem to find this side. So really what this problem is saying is use Pythagorean Theorem twice to find the missing values. And once we have those, we can solve the problem. Okay, so let's go in pink here. Let's see, we've got h squared plus 5 squared equals 13 squared. You might remember this Pythagorean triple. If not, let's do the arithmetic. So this is plus 25 equals 169. Subtracting the 25, we get h squared is 144. Square rooting, we get h is 12. So the height here is 12. Okay, so we found the missing height. And now we can go over to the right side here and say, okay, well, in this right triangle, I've got this missing side, a height of 12, and this is 20. But you know what? Before I go ahead and use Pythagorean Theorem, I noticed that I could divide a 4 out of both of those. So I'm going to use the smaller, similar triangle. That is 3 and 5. And oh my gosh, I don't need to use any Pythagorean Theorem. I know this is a 3, 4, 5 triple. So multiplying, whoa, that's crazy. Multiplying by 4 to get back up here, I get 4 times 4. I get that missing side is 16. So the second base then is equal to the entire length on the bottom here. So the second base is 5 plus 15 plus 16, or 20 plus 16, or 36. So I put 36 in here. And then it just becomes arithmetic. So what I'm going to do is I'm just going to move this down a little bit. And so simplifying here, I've got, let's see, 1/2 of 12 is 6 times, and then multiplying this parenthesis, or I mean adding these things in the parentheses, I get 40, I get 51. So 6 times 51, that means the area is, well, 6 times 50 is 300, and then one more 6, so that's 306. Again, you could just use a calculator too. All right. Now the perimeter is easier. Off to the side here, I'll do it up top. The perimeter is simply just, let's start at a corner and just go all the way around the shape. So it's 15 plus 20 plus 60. Oh, well, we know the whole base on the bottom is 36. We just figured that out. So let's just do the bottom base is 36 plus the other side is 13. So those are the 4 sides. So we've got 35 plus, and this becomes 49. So that's 70 and 14, so that's 84. So the perimeter is 84. All right, so now going over to the right here. Well, I noticed from the markings that this must be a kite. Okay, I'm going to blow this up a little. And one of the things we know about a kite, probably the single most, or actually I'd say there's two most important things. One is we have a line of symmetry across here, and that cuts everything in half. So that means this angle is cut in half, which means this angle must be 90 degrees each. Okay, and then everything matches. So, right, this angle matches this, this angle matches this, and so on and so forth. But we don't need all that, okay? So, we do know, though, that those are right angles in the middle. And what that means is we can use the symmetry and say, okay, well, I know there's a 25 here because of the marking. I know there's a 35 here because of the marking. And if that's 20 right here, then this is 20 down here because it's that line of symmetry. So all I've got to do is use some Pythagorean theorem to find this missing chunk and this missing chunk. And then I could find the area into, oh, let's just find the perimeter. Shoot. So the perimeter is just 25 plus 35 plus 25 plus 35. So it's, let's see, that's 50, that's 60 plus 60. So the perimeter here is 120 before we go any further. But so the area we could do in two ways. The area we could just look at this as either two triangles, right? We could look at like this triangle on top and then multiply that area by 2. Or we could find the area of this triangle plus the area of this triangle plus the area of this triangle plus the area of this triangle. So we've got all sorts of ways we could use it. Or from our notes, we could remember that the area of a kite and a rhombus is diagonal 1 times diagonal 2 divided by 2. And we already know that one diagonal is 40 long. So if we could just find that second diagonal, we've got it. Okay, so really what we're looking for here is, can we find that second diagonal? So let's look for it. We need to find this length and this length. Both of those can be found using Pythagorean theorem. So let's do the first one here is, I've got 20 and 25, and I'm looking for this. Well, again, before I use Pythagorean theorem, I'm going to simplify this triangle. I'm going to say, well, that's similar to 4 and a 5. And so, oh my gosh, this is another 3, 4, 5 triangle. So just multiplying by 5, that scale factor between these two similar triangles, I get that this side must be 15. And you could have found that using Pythagorean theorem. Okay, so we've got part of this diagonal. Now, it's not the case that this kite is symmetrical over this line. It does not have two lines of symmetry, so you cannot say the other half is 15. These are two different isosceles triangles. Here's one isosceles triangle that is its own height at 15, and here's a totally different isosceles triangle with a different height. If they were the same isosceles triangle, this would be a rhombus. Okay, and a kite is specifically not a rhombus, so these must actually be different lengths. They cannot be the same. So over here, let's figure out, okay? We've got 20 as the height. We've got a 35 here. So again, I'm going to say let's take out a 5. Okay, so taking out a 5, we get a smaller version to deal with, which is a 4 and a 7. Now that's not a nice Pythagorean triple, but we can still use Pythagorean theorem to find this. Let's call it x. So x squared plus 4 squared equals 7 squared. X squared plus 16 is 49. Subtracting, we get x squared is 33. So square root, we get x is square root of 33. Okay, so we have, this is the square root of 33 right here. So times 5. We get that this is 5 root 33. And absolutely, you could approximate that. I wouldn't do it till the end of the problem. But you could say 5 times square root of 33 is 28.722. Okay, so that's around 28.722. All right, so the entire second diagonal, right? The area is the first diagonal times, and the second diagonal is going to be that 15 plus the 5 root 33, and that's all divided by 2. Okay, so all we need to do is put that into a calculator or simplify it. I like simplifying, so what I'm going to do is I'm going to say, all right, well, I can divide the 40 by 2, and I can say this is 20 times 15 plus 5 root 33, and you cannot, absolutely cannot combine these to say that's 20 root 33. That's like saying 5 plus 2x is 7x. Those are two distinct different values. This is the number 5, and this is two copies of something. That's like saying 5 apples and 2 oranges is 7 oranges, right? You can't just blend those two things together. If you're counting two distinct things, I'm counting I have 5 1s and I have 2 x's. X might be 7. So saying I have 5 1s and 2 7s, you can't just say I have 7 of something. So anyways, I digress. So let's multiply this in. So our area is exactly 15 times 20, that's 300, plus 100 root 3, that's exactly, or we go over here, we say 300 plus 100 times root 33, and what we get is 874. I'm going to round that to 2 decimal places, 46. So 87446. So 87446. All right. So again, it came down to finding those missing pieces. All right. So let's go on. All right. So down here, let's look to the next one. So first, let's find the area and perimeter of this. Well, the perimeter is going to be the easiest. So if this diameter of this circle is 1, then this is 0.5 or 1/2. I like fractions, so let's go with 1/2, and 1/2 is the radius. So I know that the total circumference of this would be 2 pi r, right? That's the total circumference. So the total circumference would be 2 times 1/2 is pi. But I've got a half a circle. So the length of this arc, which is half the circle, is 180 out of 360, or half the circle, times the total circumference of pi. So that's 1/2 of pi. So the entire perimeter of this shape, if I start anywhere, let's start at this point, is I go half the circumference of this circle, which we just found, plus 1 plus 1. So the perimeter is 1/2 of pi plus 1 plus 1, or the perimeter is pi over 2 plus 2. And we can absolutely approximate that. So pi divided by 2, and then we add 2. We have 3.57. All right, so over here, right, oh, sorry, the area of this, I'm sorry. So first we need to say, well, I've got half a circle. So 180 out of 360, that's 1/2, times pi r squared, and in this case, r is 1/2. So that's the area of the half circle. And then I'm going to add the area of the triangle. Now the area of the triangle is 1/2 base times height. And so going down here, I've got 1/2 of pi, and 1/2 squared is 1/4, plus 1/2 the base of the triangle. If we count this top side as the base and we look for this height, well then we know the base is 1. All we need to find is that height. And so this really comes down to that same type of problem on page 1 and the same type of problem we're going to do in the next one, which is cutting an isosceles or equilateral triangle down the middle. So going down here, we've got, just to simplify this one more step, we've got 1/8 of pi plus 1/2 times and whatever that height is. We're looking for that height. Okay, so off to the side, let's find that height really quick. So drawing this triangle, well, that was a terrible drawing. Let's see. Okay, this is equilateral, so I know all the angles are 60, all the sides are 1. When I cut it in half, I get half of this 60 on the bottom is 30 and 30. I know I get right angles, and the 1 is cut in half to be 1/2 here and 1/2 here, and I'm looking for the height. Now you could use trig, you could use Pythagorean theorem. Personally, I'm going to use 30, 60, 90 triangles because I enjoy using those. It's a shortcut for me. So here's 60, right angle, 30. I have 1, 1/2, and height. And this is similar to, oops, I'll draw my other one that I have, which is 60, 30, and then my normal one is 1, 2, and √3. So what I could notice right now is to get from this triangle to this triangle, I thought I switched to pink, to get from this triangle, the scale factor was I divided by 2, or it's a 1:2 ratio. So if I have √3 here, then h is just going to be √3 divided by 2. So I'm just going to put √3 divided by 2, and I'm done. The area of this is pi divided by 8, or 1/8 of pi, plus, and then multiplying these fractions is top times top and bottom times bottom, so √3/4. So there is my exact area, or I can say that's approximately, and over here I'll say I have pi divided by 8 plus √3 divided by 4, and that ends up being 0.83. All right. So the next one is find the area of the regular polygon. This is a really common problem. They might give you the apothem to start, or they might give you that radius. They might give you a single side length, but they'll give you one thing probably. I have to give you two to be generous. Okay, so I know that the area of this is 1/2 apothem times perimeter. Now, I don't have a single side length, and I don't have the apothem. So those are the two things I'm going to look for right away. So the first thing I'm going to do is I'm going to say, okay, well, if I connect the center to this vertex over here, I know that this angle up top is 1/5, because if I were to connect all these, right, I get 1, 2, 3, 4, 5 congruent angles, because this is a regular polygon. And so 5 congruent angles here, I'm going to say that angle is 360 divided by 5, or that angle is 72 degrees. And what I'm really looking for here is half of that, because that will cut down the middle here, and I can get my apothem, and I can get, let's call this x, which once I get this length, I can say, okay, multiply it by 2 to get a single side, and then multiply it by 5 to get the entire thing. So again, what this whole problem really comes down to is, can I take a right triangle, or not right triangle, an isosceles triangle or an equilateral triangle, and cut it in half, and either use Pythagorean Theorem or trig to find the missing values. So here I've got a 36-degree angle up top and a 4 here, and I'm looking for both the apothem and let's call this x on the bottom. Okay, so I know that the cosine of 36, that would be my adjacent side here over my hypotenuse, and then this would be my opposite side, which we're not using right now. But we'll say the cosine of 36 is equal to my adjacent side over my hypotenuse. So if I multiply by 4 on both sides, I get that my apothem is 4 times cosine of 36. Okay, so I already got my apothem. So if I go down to my area, it's going to be 1/2 times, and I know my apothem is 4 times cosine of 36, which absolutely you could approximate. That is, let's see, 4 times cosine of 36. That's 3.236. Now notice I would keep a longer decimal than this in the middle of the problem if I'm going to use it, but actually I'm just going to keep the exact value because I prefer to work with that. Okay, so now I'm going to go back to pink here and I'm going to find x. Okay, so x, or sorry, not starting with x. I'm going to say the sine. I could use tangent now that I have a, but then I'd have to use this value here. So I'm going to use the simpler 4, and I'm going to say the relationship between x and 4 using this angle is opposite over hypotenuse. So opposite over hypotenuse, that's my sine. So the sine of 36 degrees is equal to my opposite over my hypotenuse. Multiplying by 4 on both sides, I get that x is equal to 4 sine 36. And again, you can approximate that. You can say 4 times sine of 36 is 2.351. Is that right? 2.3, yes, okay. Whoa. Sorry, 1 second. There we go. All right. And so down here, I'm going to say, well, I didn't need 1/2 of a side. I need the perimeter. So what I'm going to do is I'm going to say my perimeter is, well, first I need to say 2 times x. That's one side, right? And then how many sides do I have? I'm going to multiply that by 5 because I've got 5 sides, right? Number of sides. So 5 sides times the length of one side. That's the same as 5 times 2 is 10x. And if I multiply 10 times x, I get that the perimeter is exactly 10 times, and I put in that 4 sine of 36. And so I get my perimeter is exactly 40 times sine of 36. Or I get that the perimeter is approximately, and I could just move the decimal place 1 over, but I'm going to use the original value because, I don't know, maybe I'm going to have to round this 1 to a 2. So let's just double check here. So 40 times sine of 36. And no, I did not have to round that next decimal, so 23.51. But you notice how I use the original just in case there was going to be a rounding error by shortening it in the middle. So there's my perimeter. And again, I'm going to choose to put in the exact value. I'm going to put in the 40 times sine of 36. I'll use pink here just to show that I'm substituting it in. So I found my perimeter is 40 times sine of 36. Or you could just use a longer decimal. You know, use like 4 decimal places in the middle of the problem and only round when you get to the end. Again, I prefer using the exact ones, and that'll benefit you next year when you're in Algebra 2 or Trig. Okay, so let's see. So 1/2 of 4 is 2. And so 2 times 4, that gives me 80 times sine of 36 times cosine of 36. That's the exact area, and that is approximately, just going over here, I get 80 times sine of 36 times cosine of 36, and that's 38.04, so round 38.04. Okay, so we got one last page to work on together, going down here. So again, I give you one last problem here. Oh no, there's 2, where you're cutting that isosceles or equilateral triangle in half. So this one right here, solve for x in the regular polygon below. So what we've got here is, I should have said this is the center of the shape that you're dealing with. So if you start at that center of the shape, we've got a 360 degrees cut into 3 congruent pieces. And so we've got 120, 120, and 120. Now, again, since that's the center, and this is a regular polygon, each length here is x. And so it really comes down to splitting that down the middle. It's an isosceles triangle. We get that perpendicular bisector. So we get a 9 here, a 9 here. This becomes a 60. And so we've got yet another 30, 60, 90 triangle. And it looks like this. So we've got 60, 30, x, and 9. And then I'm going to, again, use my 30, 60, 90 triangle rather than going with trig here. So I'm going to say that's similar to 60, 30, and my stock one is 1, 2, and root 3. This time I don't see an easy relationship. Like, what did I multiply root 3 by to get 9? I could figure it out, but that's not easy for me. So let's just set up a proportion. Let's say x is to 2, right? X is to 2 as 9 is to root 3. As 9 is to root 3. Okay, so x is to 2 as 9 is to root 3. Now I'm just going to say, well, I could either cross multiply or just multiply by 2 to get x by itself. So 2 over 1. So I get that x is equal to 18 over root 3. Now we need to rationalize the denominator, so let's multiply top and bottom by root 3. So that's equal to 18 root 3 over 3, or x is exactly 6 root 3, which would approximate to 6 times root 3, 10.39. Perfect. Okay, graph the circle given by the equation below. Okay, and again, I made one small change here. There was a slight typo, so your printed version might have a 14 there, depending on when you printed it. So the formula used here is x minus h squared plus y minus k squared equals r squared. So right away I can see what number squared makes 16. Our radius is 4. Okay, and then the center is what values are there for h and k. So our center being this value, comma this value, where center is hk. And so the center would be 2, and then what number did I subtract to get plus 3? Well, that would be y minus negative 3, because minus a negative would be y plus 3. So our center is 2 comma negative 3. So going over here, I would just say I've got at 2 comma negative 3, so a center here at 2 comma negative 3, and a radius of 4. So what I do is I go horizontally and vertically 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then I just sketch it out. It should be, knowing what I know about tangents, that the tangent should be perpendicular to the radius at all these points. I know that it should go around like this, come down and be going vertical, come over and be going horizontal. And so there's a quick sketch, and absolutely you could use a compass to do a better one. Okay. So if the area of sector PAB below has an area of 100, then what is the radius of the circle? Well, I know the fraction. The big idea here is the fraction of, let's zoom this in, the fraction of degrees, right, out of 360, so 80 out of 360, that's the same as the fraction of the areas, right? And I could use a proportion to solve that. So let's go ahead and do that. Let's say, well, I know I've got 80 degrees out of 360. That's the slice of pie I've got. That's the percent of my circle I've got, the fraction of my circle. Well, that's equal to, and I'm just going to say I have a wedge that has an area of 100 inches squared, and I'm just going to find my whole area, right? This is the area of the total whole circle. And then I'm going to use that to find the pi r squared. Now, there are other methods here. You could straight say, well, 80 over 360 times pi r squared equals 100. So fraction of the total area equals 100, and just solve for r. I'll do it in 2 steps, okay? It's okay to do it either way, obviously. So let's cross multiply. We get 80a equals 100 times 360, dividing by a on both sides. This time I'm just going to, rather than simplifying, I'm just going to find out what decimal that is. So 100 times 360 over 80. We get exactly 450. Okay, so we've got the total area is 450, so of the whole circle. So well, I know that the area is pi r squared, so I'm just going to say 450 equals pi r squared, and I'm going to solve for r. So I'm going to first, and this is really just analogous, this is like saying 5 equals 2x squared. Pi is just a number. So I'm going to divide by that 2 first, and then I'll square root it. So let's divide by pi on both sides. We get that r squared is equal to 450 divided by pi. And then the radius when we square root is just equal to the square root of 450 divided by pi, or the radius is around, and let's figure that out. So 450 divided by pi, 143.24. 143.24. Whoops. Okay, so one last problem here. The big idea for how you would solve this problem to find the area of the shaded region is we would say, okay, well, what's the area of that fraction of the circle, that wedge, right, that sector? And then let's take away the area of that deleted triangle. Okay, well, the area of the sector is going to be what fraction of the circle do I have times pi r squared, which is the total area of the circle. So pi 24 squared, that's the total area of the circle. And I've got 120 out of 360. So, okay, so I've got the area of the whole wedge. But now I need to delete this triangle because this isn't part of it anymore. Somebody cut this out, removed it. So what I need to do is figure that out. So I've got, okay, shoot, minus 1/2 base times height. And I don't have the base or the height. So this really comes down to that similar situation we've been dealing with. This is a radius, so it's an isosceles triangle. So I have a 24, a 24, and a 120, which I will cut in half. And I will get 60, 60, 30, 30. And again, I'm going to use 30, 60, 90 triangles because those are easier for me. So I'm going to say, all right, well, from...
Test, 1, 2, 3. Test, 1, 2, 3.
All right, so 24 with a 60 and a 30. I'm going to say that's similar to my standard 30, 60, 90. That is 1, 2, and root 3. Oh, okay, sorry, I had a technical glitch there. Coming back. So I noticed that after setting this up, I've got an easy scale factor of 2 to 24 being times 12. So I noticed that 1 times 12 is this side, and root 3 times 12 is this side. So going back up, I got 12 root 3, 12 root 3, and a height of 12. And coming down here, I can plug those in. I can just simplify this by plugging it into a calculator and getting 192 pi. That's just 120 divided by 360 times 24 squared. And I'll leave the pi out. I get 192 minus, I get 1/2 of, and the base is 12 root 3 plus 12 root 3, or like 12x plus 12x. That's 24 root 3. Times the height is 12. So just simplifying that, what I notice is 1/2 of 24 is 12, and 12 times 12 is 144. So I get 192 pi minus 144 root 3, and we can approximate that to be around, just plugging that in here, I get 192 pi minus 144 root 3. That comes out to be 35377. So 35377. And that's it. I hope you enjoyed the video. If you have any questions, ask in class.